Now let's couple the efficient coding in space and color. Now we have n spatial locations, x1, x2, all the way to xn. And at each location, there are 3 cone types, R, G, B, for red, green, and blue. Therefore, the input vector has its components indexed by both R, G, B, and by space, x1, x2, all the way to xn, and again for the green, and again for the blue. So red, x1 to xn, green, x1 to xn, and blue, x1 to xn. And similarly, the output vector could also be 3n dimensional, and again indexed by space, x1 to xn, and x1 to xn, x1 to xn 3 times. And then these first indexes, 1, 2, 3, they correspond to the space RGB. So to transform this input to that encoded output, we need a 3n by 3n encoding matrix K, and each of its element is indexed by a pair of indices. Its row index is corresponding to these index. So it's 1x1, 1x2, all the way to 1xn, 2x1, 2x2, 2xn, 3x1, 3x2, all the way to 3xn, corresponding to these indices. Its column index, it's by the second pair of indices, rx1, rx2, rxn, all the way, yeah? And gx1, gx2, all the way to gxn, and bx1 all the way to bxn, corresponding to these indices. So this matrix, encoding matrix, encodes the 3n dimensional input to 3n dimensional output. To determine what should be this transform K, we need to know what is the correlation matrix for this 3n dimensional vector. So therefore, the correlation matrix is a 3n by 3n correlation matrix, and here is one element in this correlation matrix. Yeah, it's for a correlation between a cone type C at location x1 and cone type C prime at location x2, ensemble averaged. Yeah, and so this correlation, if we can write it as a factor, multiplication of 2 factors, one factor takes care of correlation between the 2 cones, C and C prime. Okay, we use this superscript bracket C to mean that this is just for the color. Correlation of the signal just for the color dimensions between cone C and cone C prime. And this is to take care of the spatial correlation with the superscript bracket X, and between location x1 and x2. And turns out that in space and color correlation, this kind of writing out into 2 factors is indeed the case in natural scenes. Now, if so, for the whole matrix, whole correlation matrix, 3n by 3n matrix, now it can be written as a tensor product between an 3 by 3 matrix, taking care of only the color correlation, which we're already familiar with in color efficient coding, and a n by n correlation matrix, which we have also learned for efficient spatial coding. And remember, this is a topless matrix. Okay. Now let's show intuitively how this should be done. And this intuition is actually correct because it can be proven analytically. You can see it in the book or the rest of the later part of this video. Okay, we start with 3 cone images. Okay, so the red cone image is a function of space x, and green cone image is a function of space x, and the blue cone image is a function of space. And we first of all just do the decorrelation in these color dimensions, or 3-dimensional color. And this we have already learned in efficient color coding how to do it by a rotation in 3D space. This rotation matrix, we have learned exactly the same rotation matrix as we have done as if there was no space. Okay, so at each location X, you do this rotation. To luminance channel, red minus green contrast channel, and blue minus yellow contrast channel. And each of these are a spatial image now, but they are decorrelated from each other. And next, you do spatial efficient coding for each of these channels in parallel and separately. Okay, and this we also have learned how to do for efficient spatial coding. So we get this efficient spatial coding filter. Okay, so for instance, for the luminance channel, because the signal noise can be very high, so this must be is likely to be a center surround resistive field. And for the chromatic channel R minus G, the signal noise could be lower, and so this perhaps is going to be more lower pass compared to that. And similarly for blue-yellow chromatic channel, it's going to be a lower pass compared to the luminance channel filter. And this gives us three efficiently coded, spatially efficiently coded three separate channels. Now you can then do the multiplexing in color dimension, and this we have learned in efficient color coding. It's just a 3D rotation in a color space, which can be, for example, the inverse of this three-dimensional rotation. Yeah, and you take this out into this encoded form, which is efficiently coded both in space and in color. Now, these are just the conceptual steps. So of course, this step and that step and that step in reality can be put together in a single phenomenological steps or many multiple steps in cascade, resulting in an effective transform, as we just have mentioned. It's a 3n by 3n matrix, transforming a 3n vector to another 3n vector. And this matrix can be decomposed into these conceptual steps. Yeah. Let's look at a simpler case to get more intuition. In this case, we only have two cone types, red and green, and let's approximately treat them as to have the same signal power in red channel and green channel. And we have learned that to decorrelate these two in color will give us these kind of a rotation matrix to give us a luminance channel and a chromatic channel. Luminance channel is red plus green, and chromatic channel is red minus green. And these two images can now be in parallel efficiently spatial coded by this filter in the luminance channel and that filter in the chromatic channel. And this filter is likely to have a center surround resistive field types as a bandpass filter, because the luminance channel has a higher signal power, while this filter is likely to have a lower pass smoothing filter, because the chromatic channel is likely to have weaker signal power. And this kind of a bandpass filter will have this bandpass looking contrast sensitivity curve, while this one is more low pass looking contrast sensitivity curve. And such contrast sensitivity curves have been looked at in human visual psychophysics as like this. Now with these kind of a efficiently coded form, now you can do the multiplexing in the two-dimensional color space, and this particular two-dimensional rotation is in fact the inverse of this, which happens to be the same as that itself. With that, you see it's 1, 1 is adding these two together, 1 plus the other one adding together. You get this as one of the channel output, and the other is 1 minus 1, difference between them, and that's the other output. So these are really the two filters adding together and the difference between these two filters. Now let's look at it in more detail. First of all, I'm going to copy this resistive field to this one-dimensional simplified form. Just take a cross-section. Space is along horizontal axis in a one-dimensional retina. So center surround resistive field in a one-dimensional space become this one. Red plus green is because this is for a luminance channel. So at each spatial location, X is for in the center is red plus green excitatory, and surround is red plus green inhibitory. Similarly, let's copy down this chromatic filter to its one-dimensional form. At each location along the horizontal axis, it's red minus green, a smoothing filter. Now let's do this multiplexing. This is to add these two filters together to get one output channel, and second row subtracting these two from each other to get the second output channel. And this will do, add these two together for one output channel and subtract these two from each other for the other output channel, and this is the result. Now let's work it out. One dimensional, at center location we have red plus green excitatory and red minus green excitatory. So plus green and minus green, green cancel out and red more or less dominate and green almost cancel out. So we have center red dominantly excitatory. Surround we have red plus green inhibitory, and here red minus green excitatory. So therefore red almost cancel each other out, and we have inhibitory green dominating at the surround. So we have red center, green surround. Similarly for this, you can work it out. If you subtract these from each other, you will get green center excitatory and red surround inhibitory. So red center excitatory, green surround inhibitory, and vice versa. This is showing the resistive fields in two-dimensional space for this one-dimensional form, two-dimensional space, and this is for that form. And they are very similar to the shape in two-dimensional space, except now it's color-coded. And so for this cell, it's red center excitatory, green surround inhibitory. And this is the other way around, green center excitatory, red surround inhibitory. And these are indeed the resistive fields experimentally observed in the retinal ganglion cells. If you replace red and green by blue and yellow, you will get analogously the same result, with blue center excitatory, yellow surround inhibitory, or vice versa. Yeah, and so these are the kind of resistive field also people have observed in the retina. Now, these are intuitive steps of how we do the color space efficient coding coupled together. If you like to know the mathematical background supporting this intuitive way of looking at things, you can continue with this video, or you can read the textbook for more details. Now let's add some mathematical background to the intuitive steps just mentioned. Remember that our correlation matrix in color and space can be factorized into two matrices. One is for color correlation only, and the other is for spatial correlation only. And we have learned from efficient color coding that a three-dimensional 3D rotation matrix, KOC, C for color, can diagonalize this correlation matrix. This means, this is a decorrelation matrix for that, and this means that its row vector, each of its row vector is an eigenvector of this matrix. So you add this matrix onto a row vector, you can get this eigenvector, again this row vector with the corresponding eigenvalue. Okay, and similarly, this spatial correlation matrix can be decorrelated or diagonalized by a spatial transform, which is a Fourier transform we have learned from efficient spatial coding, and such that its row vector, let's say its kth row vector, is an eigenvector of this correlation matrix with its corresponding eigenvalue. And we remember that this row vector is a Fourier wave of spatial frequency k. And now you can prove that for this general 3n by 3n matrix, the corresponding decorrelation matrix is KO, made from tensor product of this color decorrelation matrix and a spatial correlation decorrelation matrix, and you put them together, okay, tensor product, such that it's one of its row, each one of its row vector, let's index. Well, first of all, this row vector is made from a row vector in here and a row vector in there. So it's kappa's row vector in here and k's row vector in there. Explicitly write it out. You can see that, yeah, again, kappa k indicate the row, and each of its element is indexed by color index and space index. So color, space, red x1 all the way to red xn, and g x1 all the way to g xn, and blue, B for blue, blue x1 to blue xn. Now let's show that this whole vector, row vector, is indeed an eigenvector of this whole correlation matrix in both space and color. Now let's write it out. Yeah, this whole correlation matrix is written this way now in all its components acting on this row vector. Now remember, this correlation can be factored out into a correlation factor in color and another correlation factor in space, yeah, as we have noted here. And similarly, this row vector really is a row vector in color and row vector in space, just like it's written here. Now we group the color component, correlation in color and row vector in color together, and we grouped the spatial component together, so correlation in space and row vector in space together. Now since this is an eigenvector, yeah, as we have seen here, so therefore it's equal to that. And similarly, this is an eigenvector in space like we have seen here, so it's like that. Now we get this outcome. The two eigenvalues multiply each other, and the two eigenvectors by definition is this row vector. So this proves that this row vector is indeed an eigenvector of this whole correlation matrix, yeah, in both space and color, and the eigenvalue is the multiplication of the two eigenvalues. We can now project our original input in color and space onto this eigenvector. This will give us the coefficient, which is the principal component for this eigenvector. Yeah, if we write it out again, factor out into the row vector in color and space, and put the color term here, grouping together. This is grouped in color, and this is the rotation in space, the transformation Fourier transform. And therefore you see that this is a color decorrelation into luminance or chromatic channels, and this is then the Fourier transform can go to this component, which is for the kappas and the K frequency. Kappa is luminance or chromatic, red, green chromatic, or blue, yellow chromatic. And we know from here that the average variance power is equal to the eigenvalue. Now we can apply our usual recipe to see that our coding, efficient coding K transform is having these decorrelation, this gate control, and this multiplexing, coupling space and color. And this is the mathematical background for the intuitive steps of coding we introduced a few slides earlier.